Welcome everyone. Today we are here to present an in-depth analysis of the Blackbird engine, especially the Pratt Whitney J58 engine. This aircraft is also known as SR-71 Blackbird. So my name is Moin Ashfaq Mullah and I will be covering the introduction and air intake system of this engine. The SR-71 Blackbird aircraft was one of the most advanced reconnaissance aircraft ever built, which has capable at flying at Mach number 3.2, which is around 3,540 km per hour. It can fly at an altitude of 85,000 feet, which is around 25,900 meters. To achieve such extreme performance, it required a highly specialized engine, which is known as the Pratt and Whitney J58 turbojet engine. This engine was unique because it is operated as a turbojet at lower speed, but uh, transit, transmitted the ramjet like engine at supersonic speed, making it one of the most advanced propulsion system of its time. This aircraft was now not in sale. Which, so now let us discuss the first key point of this engine, which is the air intake system. It is an first component of engine. The air intake is crucial because it regulates airflow into the engine, maintains stability and efficiency at different speeds. At supersonic speed, controlling airflow is a major challenge because of the shock wave that form in front of the engine. To solve this, the SR-71 used a complex spike inlet design that moved backward as speed increase when the speed increased, helping them to slow down the incoming air before it entered the compressor. This was necessary because jet engine cannot handle at supersonic airflow directly. Another key aspect is airflow dynamics. Engineers use the computational fluid dynamics (CFD) for a simulation to optimize the pressure recovery and minimize energy losses, ensuring that the engine receives the correct amount of the compressed air. So, without this highly efficient air intake system, the engine would stall or fail at high speed. Now, my friend Pranav will explain the next important component, which is the compressor and combustion chamber.
Thank you, Moin. Now let's move the next major component, the compressor. The compressor main function is to increase pressure of incoming air before it enters to combustion chamber. This is essential because higher pressures allows more efficient fuel combustion, resulting in greater thrust. The J58 engine used an axial flow compressor, which consists multiple rotating and stationary blades that progressively compress the air. Compared to centrifugal compressor, axial compressors are more efficient for high-speed aircraft like SR-71 because they provide steady and continuous flow of compressor air. So next is combustion chamber and heat management. Now that the air has been compressed, it moves into combustion chamber where it mixes it with fuel and ignite to produce high energy exhaust gases. The J58 used to JP7 fuel, a special aviation fuel with high flash point. Since this fuel was difficult to ignite, the engine used a TEB high reactive chemical to start combustion. One of the biggest challenges in the supersonic flight is heat management. At Mach 3.2, the engine experiences extreme temperature of up to 650 degrees Celsius. To handle this, engine is implemented film cooling. A thin layer of cool air protects the combustion chamber wall from direct heat. Internal cooling passage designed with engine component to reduce thermal stress. Effective heat management ensures that engine parts do not fail under high temperature, increasing lifespan of engine. Now my teammate Om will explain how it's extracted from combustion gas and converted into thrust.
Thank you, Pranav. Now let's discuss the turbine, one of the most critical components of in power extraction. Once combustion occurs, the high temperature, high pressure gases pass through the turbine. The turbine is connected to the compressor through a shaft, meaning that as hot gases pass through, they spin the turbine blades, which in turn drive the compressor. The turbine blades must withstand extreme temperature and stresses. That's why they are made from nickel-based superalloys and have internal cooling channels to prevent overheating. Without a well-designed turbine, the engine would not be able to function efficiently. Now let's look at the final component, the nozzle. The nozzle's job is to convert high pressure exhaust gases into direct thrust, propelling the aircraft forward. The J58 engine uses a convergent divergent nozzle, which is ideal for supersonic engine. This nozzle accelerates the exhaust flow, sometimes reaching speeds beyond the Mach 3.2. One of the most important features of the J58 was its afterburner. By injecting extra fuel into the exhaust gases, it created additional thrust, helping the SR-71 escape enemy threats. Now that we have completed our presentation, let's have a short discussion on the key aspects of the Pratt and Whitney J58 engine and its impact on aviation. One of the most fascinating things about this engine is its hybrid turbojet ramjet operation. Unlike conventional jet engines, the J58 was able to switch modes during flight. Pranav, can you explain how this transition works?
Yes, Om. The 50 jet engine operated traditional turbojet at lower speed, meaning the compressor and turbine played a major role in maintaining airflow and pressure. But as the aircraft approached Mach 2.5 and beyond, the bypass system redirected more and around the compressor, effectively reduced the turbojet workload. That allowed the engine to behave more like a ramjet, using forward motion of the aircraft itself to compress incoming air. This was one of the biggest engineering challenges because normal jet engines cannot function efficiently at such high speeds. That's why the SR-71 could sustain Mach 3.2 speed for long duration. But this also introduced significant heat management challenges. Moin, can you elaborate on how the engines handled extreme temperatures?
Absolutely, Pranav. Heat management was a huge concern because at Mach 3.2, the airframe and engine component would experience temperature exceeding 1200 Fahrenheit, which is around 650 degrees Celsius. The JP7 fuel itself acted as coolant before combustion, absorbing excess heat. Additionally, the engine used internal cooling passage and film cooling technique, where cooler air formed a protective layer over a hot surface. Without this cooling technique, the turbine blade and combustion chamber would not have survived the extreme heat generated during flight. But despite all this advantage, the J58 has significant drawback. Now, Om, what do you think was the biggest limitation?
That's a great point, Moin. One of the biggest limitations of the J58 engine was its fuel consumption. At full speed, the SR71 burned fuel at an enormous rate, meaning it had to refuel mid-air multiple times during long missions. Also, the engine was insufficient at low speeds. It was optimized for supersonic flight, so during takeoff and landing, its performance wasn't as effective as conventional jet engines. But even with these drawbacks, the J58 remains the revolutionary engine. The knowledge gained from its development helped shape future supersonic and hypersonic propulsion systems. Pranav, do you think we will see engines like this being used again in the future?
That's an interesting question, Om. While modern engines focus more on fuel efficiency, there is a renewed interest in hypersonic propulsion. Technology like scramjet. Scramjet means supersonic combustion ramjets are being developed for aircraft and space travels. The J58 was a stepping stone in high-speed aviation, providing that sustained supersonic flight is possible with the right engineering.
So, in conclusion, the Pratt and Whitney J58 engine was a groundbreaking design that allows the SR-71 Blackbird to become one of the most advanced aircraft in history. Despite its challenges, the J58 remains one of the most powerful and innovative jet engine ever developed. Thank you all for your attention.